The discussion of stoichiometry, or the mathematics of chemistry, begins with a simple balanced chemical equation. It's important that we have the balanced chemical equation in front of us because this is going to give us a ratio of the moles of substances that are reacting together and the moles of products that are produced. Remember, we talked about how coefficients in front give us the ratio of particles that are reacting. For example, we have two molecules of hydrogen are reacting with one molecule of oxygen to produce two molecules of water. Well, how do we jump from molecules of substance to moles of a substance? No matter how much of each of these reactants we have, it's going to always react in a 2-to-1 ratio hydrogen to oxygen and produce 2 parts water. So just a very simple example here. If I have 4 molecules of hydrogen, it's going to need to react with 2 molecules of oxygen to react completely, and that reaction will produce 4 molecules of water. If we take this out a little bit further, no matter how much we have, maybe we have 100 molecules of hydrogen. That would mean we would need 50 molecules of oxygen and 100 molecules of water would be produced. Well, as you might imagine, it's very difficult because we're not dealing with pieces of a puzzle. It's very difficult to just put 1 or 2 molecules together. When we're working in the laboratory setting, really what's taking place is we have just a large quantity of these substances. For example, if I had 2 billion, billion's always a big number to people, molecules of hydrogen, I would need 1 billion molecules of oxygen, and I could make 2 billion molecules of water. But we work with even more than 1 billion. And as you know, or you might imagine, if I work with 6.02 times 10 to the 23rd molecules of oxygen, how much water would I need for that? Or how much water could be produced? Well, I would need 2 times 6.02 times 10 to the 23rd. So 12.04 times 10 to the 23rd molecules of water would be produced. To react with 6.02 times 10 to the 23rd oxygen molecules, I would need 12.04 times 10 to the 23rd hydrogen molecules. Well, in chemistry, we don't really want to get into all of these digits, decimals, so we can shortcut it just a little bit. Just like 12 would be a dozen, 6.02 times 10 to the 23rd we know as Avogadro's number, or 1 mole. And so we can say that if I have 1 mole of oxygen, that would react with 2 moles of hydrogen, producing 2 moles of water. And so from a molecule standpoint, we can see that we can also refer to this as moles. From this, if I have a 2 moles of hydrogen react with 1 mole of oxygen to produce 2 moles of water, we can make mole ratios. These will become conversion factors for determining if I have a certain amount of one substance, how much of another substance can be produced. You will hear me talk about these as the mole bridge. And the mole bridge comes from a balanced chemical equation. BCE, balanced chemical equation. Well, if I have three substances, I should be able to make quite a few mole ratios out of these. I know that there's, for every 2 H2, I'm going to need 1 oxygen molecule. So this can be 2 molecules, or we say 2 moles of hydrogen for every 1 mole of oxygen. As you know, with any conversion factor, it just equals 1, so I can flip this also. I could call this 1 mole of oxygen for every 2 moles of hydrogen. If I look at the ratio of hydrogen to water, for every 2 molecules of hydrogen, I make 2 molecules of water. Or, as we showed, molecules or moles, 2 moles of hydrogen would make 2 moles of water. Or 2 moles of water would produce, 2 moles of water would be produced from 2 moles of hydrogen. And then again, we could take 1 molecule of oxygen in a ratio with 2 water molecules. But not just molecules, we can do moles. 1 mole of oxygen would produce 2 moles of water, or 2 moles of water would be produced from 1 mole of oxygen. Having this information at hand, then, gives us multiple ways to interpret chemical reactions. Chemical reactions can be interpreted in terms of particles, moles, and since we can convert moles to grams, it can be converted in terms of grams, interpreted. And then we're going to take it one step further, and if we have gaseous substances, we can interpret it in terms of liters of gas produced or used. And so I can use my formula. 2H2 reacts with O2 to produce 2H2O. In terms of particles, I can say that we have 2 molecules of hydrogen react with 1 molecule of oxygen to yield 2 molecules of water. Or I can say that 2 moles of hydrogen, allow me just to use the symbols here, react with 1 mole of oxygen to yield 2 moles of water. In the next part, we'll look to see how we can turn this into grams and to liters of gas.